Let us find out the subgroup of this S3, which is a symmetric group. So now here the subgroups of S3 are H1, which contains only the identity element, that is I, or the identity mapping. H2 will be the whole of S3, and these two subgroups H1 and H2 are called improper subgroups. Now the other subgroups of this S3 are H3, which contains the identity element and this element 1, 2. You can see from this table that I with 1, 2, I with 1, 2 forms a group, because the composition of any element of this set will always be in itself. So H3 is called that I, 1, 2 is a subgroup. You can construct a table like this. This is I, this is 1, 2, I and 1, 2. So I composite I is identity. I composite 1, 2, we can check from this main table. It is 1, 2 itself. 1, 2 composite I will be 1, 2. 1, 2 composite 1, 2 is I. So this one forms a group. It satisfies all the three axioms, that is the associativity, since S3 already satisfied associative property, so H3 also will satisfy that one, since it is a subset of S3. Then identity element exists, that is I itself, and then every element of this H3 has an inverse in itself. The inverse of I is I itself, and the inverse of 1, 2 is 1, 2 itself. So this one forms a group, or satisfy the group axiom. So and since it is a subset of S3, so it will be a subgroup of S3. Similarly, H4, which contains identity element and 1, 3 also, will form a subgroup. You can construct a table like this one and check from the main table. And then you'll see that every element of this one has an inverse in itself. Similarly, H3, which contains identity and 2, 3 also, this is also another subgroup of S3. And the last one is this one, H6, which contains three elements, identity, then 1, 2, 3 and 1, 3, 2. If you check from the table, you'll see that 1, 2, 3 composite 1, 3, 2 gives you I. 1, 2, 3 composite 1, 2, 3, it is 1, 3, 2. Similarly, 1, 3, 2 composite itself, it is 1, 2, 3. And 1, 3, 2 composite 1, 2, 3 gives you I. So here this one forms a group, or satisfy the group axioms. So these four are called the proper subgroups of S3. Now we know that S3 is not an abelian group, and then what we notice from here is that H3, H4 and H3, H4 and H5 will not be a normal subgroup of S3. You can check, for example, H3 is not a normal subgroup of S3. Since you can take for any X, okay, let me just take this one. For H is equal to 1, 2, which belong to S3, and let us take X is equal to, say, 2, 3, which belong to S3. This one belongs to H. Let's correct this one. It belongs to H, and this belongs to S3. Then what is X inverse? X inverse is equal to 2, 3 into 1, 2 into 2, 3 the whole inverse, which is equal to 2, 3, 1, 2 into 2, 3. The inverse of 2, 3, if you see the table, it is itself only. 2, 3 composite itself gives you I. So therefore it will be 2, 3. And on taking the composition of this one, you'll get the element of this as, you compose this 2, and then after that the composition of this one you take with the composition of this 2, 3, and you can do it by yourself also. So it is equal to 1, 3, which is not an element of H3. Therefore X inverse does not belong to H3, for every X belong to S3 and H belong to H3. So by definition of normal subgroup, H3 is not a normal subgroup of S3. Similarly, H4, H5 also are not normal subgroup of S3. But H6, which contains this element I, then 1, 2, 3, 1, 3, 2, this one is a normal subgroup of, S3. Why? What is the index? Index of H6 in S3, using that theorem, it is equal to order of S3 by order of H6. The order of S3 is equal to 6 because S3 contains 6 elements, and H6, what is the order of H6? It is 3. Why? It contains 3 elements, so it will be 3. So this will give you 2, which means that index of H6 in S3 is equal to 2. By the theorem, if the index of a subgroup is 2 in a group G, then in that case, that subgroup will always be a normal subgroup of G. So by applying that theorem, we can conclude that H6 is the normal subgroup of S3. So this one shows that H6 is the only normal subgroup of S3. And H3, H4, H5, which are the order proper subgroups of S3, are not normal subgroups of S3. Now I'll give you one more example related to this one, normal subgroup. Now if you consider this group G, which contain the elements plus or minus 1, plus or minus I, plus or minus j, plus or minus k, then we know that this will be a group under the binary operation that defined as follows. I dot I will be same as j dot j is equal to k dot k, which is minus 1. I dot j is equal to k, j dot I is minus k, j dot k is equal to I, k dot j is equal to minus I, k dot I is equal to j, I dot k is equal to minus j. So this forms a group under the binary operation defined in this way. Now associativity, it will satisfy because for every A and B, A, B, C belong to G, A dot B dot C will be same as A dot B dot C. For example, you can take A to be I, B to be J, and C is equal to K. Then what is I dot j dot k. The I dot j by definition it is k dot k is equal to minus 1. Now let us see what is I dot of j dot k by considering the last two. So this is I dot, what is j dot k? It is I. I dot I is minus 1. So you can see that this one is same as this, which equal to minus 1. Therefore, it will if you take any other elements also, A to be minus I, B to be 1, and C is equal to minus K, and so on, it will always satisfy the condition that A dot B dot C will be same as A dot of B dot C. Existence of identity element. Now 1 will be the identity element. You can check from the table that I have already sent it through PDF, from the notes that I have already sent to you. You can check that 1 act as the identity element. That is 1 dot I will be same as I, 1 dot minus j also will be minus j, and so on. So therefore, identity element exists in this group. Existence of inverse. That means every element of G has an inverse in itself. For example, the inverse of 1 will be 1 itself. The inverse of minus 1 is minus 1. The inverse of I is minus I, because I dot of minus I gives you 1 identity. Because as I dot I is minus 1, so if you take the dot product of I with minus I, that one gives you 1 identity. So the inverse of I will be minus I. Similarly, the inverse of minus I will be I. So all the elements of G will have an inverse in G itself. So that's why it will form a group. Now these are the subgroup of this G. H1, which contains only the singleton element E, that is the identity element 1. H2, which is the whole set group itself. Then these two, H1 and H2, are the improper subgroups. Now the other proper subgroup of G here will be H3, which contains only 2 elements plus or minus 1, because you can check from here that this is 1 and this is minus 1. 1 and minus 1. 1 dot 1 is 1, 1 minus 1 will be minus 1, minus 1 into 1 will be 1, minus 1, minus 1 into minus 1 will be 1. So you can see that this one will satisfy all the group axioms. Similarly, H4, which contains 4 elements plus or minus 1, plus or minus I, plus or minus j, plus or minus k, and H6, which contains plus or minus 1, plus or minus k. These are the other subgroups of subgroup of this G. Now this one is a normal subgroup. H3 is a normal subgroup of G. Why? Because for every X belong to G, H belong to H3. Then what we have now is that H3 can be either minus 1 or 1. So if H3 is equal to 1, then what is XH? Okay, I'll just take this as H only. X inverse is equal to x into 1 into x inverse. X into 1 will be x itself because 1 is the identity element, so it will be x inverse, and this will be 1, always the identity. Then if you take h is equal to minus 1 also, for every x belong to G, x inverse is equal to x into minus 1 into x inverse. This is equal to minus x inverse, and this is equal to minus 1. You'll get it because the value of this will always be 1. So this implies that x inverse will always belongs to H3 for every x belongs to G and H belong to H3. So therefore H3 will be a normal subgroup of G. However, H4, H5 and H6, these are also normal subgroup of G. Why? For this one, we need not prove it by using the definition. Straight away, we can use that theorem on index. For what is the order of H4? Order of H4 is equal to 4. Order of G, which contain 8 elements, it is 8. Now, index of H4 in G is equal to order of G divided by order of H4, which is equal to 8 by 4, and this is equal to 2. So now, by the theorem that if the index of a subgroup is 2 in G, then in that case H will always be a normal subgroup. So here, since index of H4 in G is 2, so we can conclude that H4 is a normal subgroup of G. Similarly, you can show that the index of H5, H6 will be 2 because this contains 4 elements. The order of this also will be 4. So index of H5 in G will be order of G by order of H5, which will be 2 again. So H5 will be normal, H6 also will be normal. And what we notice is that this is an example of a group which is non-abelian. G is non-abelian. Why? Because you can see from this one, J dot I is minus K, not the same as I dot J, which is equal to K. So it is a non-abelian group, but all its proper subgroups are normal. All the proper subgroups are normal. So that means you can have an example of a non-abelian group where all the proper subgroups can be normal subgroups. Now hope it is clear regarding this example.